Okay. Good afternoon, everybody. Welcome to the Monday afternoon press conference here at the 234th meeting of the American Astronomical Society at St. Louis Union Station Hotel in St. Louis, Missouri. I'm Rick Fienberg. I'm the AAS press officer. And assisting me today, monitoring our webcast of the briefing, is my media fellow, Carrie Hensley from Boston University. If you are watching the webcast and you have the chat password, please queue up your questions for Carrie using the chat box, and then after we do some Q&A here in the room, we'll go to you on the webcast. The way these briefings work is that we'll have all the panelists make their presentations one after the other. Hold your questions to the end. That way we don't step on anybody's allotment of presentation time. And then we'll start with questions here in the room and then go to the webcast. All right, so this is a meeting of the American Astronomical Society and two of its divisions, the Laboratory Astrophysics Division, which is our newest division, and the Solar Physics Division, which is one of our very active divisions. They often meet on their own, but they often also meet with us, and that's what they're doing here. And as a result, we have a lot of talks on the sun and solar physics and the sun-Earth connection. And this afternoon's briefing is called What's New Under the Sun, and it's 4 talks all about our favorite star, the nearest star, the sun. We're going to have 4 presentations. The first will be from Sanjiv Tiwari from Lockheed Martin's Solar and Astrophysics Laboratory. He's going to talk about fine-scale explosive energy release in the core of a solar active region. He'll be followed by Karin Muglach from NASA Goddard Space Flight Center. She'll talk on the life of coronal bright points. Then we'll have Alexander Kosovichev from the New Jersey Institute of Technology. They're the folks that run the Big Bear Solar Observatory. His talk is entitled Detection of Dynamo Waves in the Solar Convection Zone by Helioseismology. And finally, something a little different from Timothy Larson, who's currently at Moberly Area Community College. He's going to speak on listening to the sun, the sonification of solar harmonics. And so with that, I will turn it over to Sanjiv, and we will get started.
Thank you, Rick. Good afternoon, everyone. My name is Sanjiv Tiwari, and I'm going to talk about fine-scale explosive energy release in the core of the solar active region observed by HI-C 2.1. That is high-resolution coronal imager 2.1. This was a successful second HI-C flight from White Sands last year. The first HI-C flight was in 2012. So we obtained highest spatial resolution and temporal resolution data ever of solar active region at 1 million Kelvin for 5 minutes. There were other instruments which actually co-observed with HI-C, and one of them is interface region imaging spectrograph, IRIS. So we used that data, spectral data also from IRIS together with HI-C to understand the smallest scale structures in the core of the active region. Active regions are the strongest magnetic field regions on the surface of the sun. They can have a strong magnetic field up to 4,000 or even more in some cases, which is about 10,000 times stronger than the magnetic field that we have on the Earth. Active regions are also hottest structures in the solar corona. If you look around the solar structure, you find any active region that will be the hottest. And not only that, the core of the active region will be even hottest among active regions as well. So this is AI-94 image. And this one maps plasma, coronal plasma at 6 million Kelvin. When you look corona at 1 million Kelvin in 171, the core of the active region, the same core that was brightest actually, that is not actually the brightest anymore. So we have small, tiny, cool structures, cool loops there. And HI-C observed this field of view of the active region, and that is where all those activities we are going to see. So this is 5-minute HI-C observation. You can look at the movie, and the field of interest that I have been working on is outlined by the blue box. So if you look carefully, there are so tiny structures, so many tiny structures everywhere in this field of view, which were never, most of them were never resolved actually by earlier observations. So we actually found 3 types of dynamic small-scale energy release events. So just to remind you, this was only for 5 minutes, and we have 4 seconds of cadence. So we have about 150 kilometers of spatial resolution, which was never obtained before. So first energy release event was dot-like structure. So these tiny dots you can see in the core of the active region, pointed by 2 arrows, if you can note. These are actually, for compare, if you compare with Earth, these are 10 times smaller than the Earth. So their diameter is 10 times smaller than even Earth. And for comparison of this field of view, you can see Earth is scaled down there. So we combined with iris data so that we have transition region information as well, and then we have coronal information in hot 94 as well. So we actually found 2 other type of very tiny scale structures, and one is these are dynamic events basically. So these are loop-like events, and there is another third one is surge-like event. So there are little differences in these events. So for example, surge-like event looks like there are dots. These are like type 1 events, but they are not, because there is plasma outflow involved, and that we found after we analyzed iris spectral data. So these 3 types of events are all, actually this was very surprising and very interesting, that they are all rooted at mixed polarity magnetic field regions, all of them. So even these tiny dot-like structures, smaller than 10 times smaller than Earth, they are tiny loops which are kind of the size of radius of Earth. They are all, and surge-like events that you have plasma outflow, they have all mixed polarity field, neutral line. So that is where your positive magnetic field and negative magnetic field meet. So you have a neutral line, and those are that is where flux cancellation can happen. So the most important result that we find that different types of activity, these small scale activities, they are all sitting at neutral line where flux cancellation is happening. When we try to see what is their thermal response, and whether they are really hot, whether we can see some responses in chromosphere, I mean cooler atmosphere, and very hot atmosphere. So we found that, and basically the idea was to see whether they are similar to solar flares. You must have heard typical solar flares. They have very hot response in the beginning, and then there is a cooling sequence. So that kind of light curve we don't see. Light curve means we plot intensity with time. We don't see that kind of response here. So these are not typical flares. They are more different kind of events. So we used high C 2.1 observations to obtain the highest spatial resolution and temporal guidance data, where we found the tiny actually not nanoflare, but really tiny microflares. And we, by combination of high C and iris, these provide actually new insights into how the solar atmosphere responds to the surface magnetic field evolution. We found 3 types of events, and they are all seated at neutral lines. So this is kind of very interesting that even tiny scale events are rooted at mixed polarity field, and there is flux cancellation that is happening. So we proposed actually new formation mechanism of these events, which has to be confirmed with MSD simulations. Thank you.
So good afternoon. My name is Karin Muglach. I'm giving the second presentation here, and the title of my talk is The Life of Solar Coronal Bright Points. I would like to acknowledge also my coworker here, Andrew Leisner. He was a student at Goddard Space Flight Center last summer, and he continued working with me. And he was doing most of the hard work of collecting all the data and data processing. So what you have just heard before a little bit is about solar active regions, and I would also like to start off with that. So you see here an image of the sun, actually a movie of the sun taken with a solar dynamics observatory in the wavelength of 193. And this represents the corona of the sun at a temperature of around 1.5 million Kelvin. The movie that you see is 12 days. So this is now kind of very slow evolutionary development that you can see in these active regions. So all the bright regions that you see are hot magnetized plasma. And you can also see from this movie that every now and then you see some strong brightening flashing up. And you can also see then sometimes, together with these flashes, that the corona opens up and you have an ejection of mass here. So solar eruptive events, in particularly flares and coronal mass ejections, are usually found in these active regions, in these hot magnetized plasmas. Now, everything of this activity is basically driven by the magnetic field, and you can imagine the magnetic field as a kind of large-scale, three-dimensional structure. And part of this structure we can see in this emission in the coronal lines. But there is only one place at the moment in the solar atmosphere where we can actually measure the magnetic field, and that is at a lower level. This is in the photospheric level. And so let me show you now a photospheric image. And actually, the same 12 days of data, oops, sorry. And the same 12 days as a now magnetic movie. So you see now black and white areas, which are basically, you can imagine you have your coronal magnetic field, which goes down into the photosphere, and of course it has a plus and minus pole like it would be for a magnetic field. And you can see that within these 12 days, these active regions move around, move over the solar disk, and then actually disappear here. So let me state the problem now, and that is, the solar activity that we see is intimately connected to the solar magnetic field. We can only directly observe it and measure it in the photosphere. A lot of the activity, though, is up in the corona. These eruptive events are, generally speaking, represent a conversion of the magnetic field, or the magnetic energy, into the kinetic energy and thermal energy of the plasma. So you have magnetic energy first, which is converted into heating as well as flows in the plasma at higher layers. So this is kind of about the level of agreement in the solar community. The disagreement is then now in the details. And one of the questions then that comes up is, how do we build up the energy in these active regions or magnetic systems? And then, of course, how, when, and why is the energy then released in these flares or coronal mass ejections, these eruptive events? And as you have seen in the two movies I showed you before, one of the problems is that the sun is rotating, and the lifetime of these large active regions can be several days, weeks, even months. And that means they emerge, and then they rotate off, and then we have to wait about 20 days until they come back so that we can measure them again in terms of the direct measurement of the magnetic field. So any kind of active region, we only see bits and pieces of them if we want to study the magnetic evolution of them. And what I'm trying to suggest here, and the aim of the project I'm doing now, is how about scaling the active region down to smaller and smaller size? Because it turns out the smaller the size, the slower or the shorter the lifetime. So if I have now a very, very small active region, a kind of tiny miniature active region, it only lives a few days. And this is exactly the time scale that I need so that I continuously observe this miniature active region from its beginning, the very birth, all the way to its death when it disappears. And these coronal bright points that my title is all about is kind of like a miniature active region. So in this case, I can now really study the magnetic field evolution from the very beginning all the way to the very end. And the idea is then, what can I learn from these miniature active regions that can I then transfer to the large-scale active regions, and how do they form, how do they get energized, how do they release then the energy in eruptive events. So the way we have been doing this is we have been looking at these coronal bright points, and we have selected lots of them now. We have something like 70 of them, where we looked at the complete time evolution. This is an ongoing project. It's in progress, and so I can only give you now a kind of flavor of the first results that we have seen, and I will show you 2 of these examples. We are going to use the data from the Stellar Dynamics Observatory, again in the coronal line 193. We also added another filter, which is 304. This is in the layer which is between the photosphere and the corona, which is a chromosphere. So this has a kind of medium temperature plasma that you can see there. And in the lower photosphere, we're looking at magnetograms at the moment mostly, but we're also working on using intensity images to get additional information on the evolution. So let me give you now a better feeling of what are the spatial scales we're looking at. Remember, you just saw the big active regions, which cover a good fraction of the solar disk. What I'm looking at here is, you see the red box is my target region, and you see then very small regions that are point-like within this box here. And to zoom in a little bit more, you can see now here, these are the sizes of these coronal bright points. You see the red circles, but we have put around it. And this is a sample of 4 of these coronal bright points that we looked in this particular field of view that you can see here. As I said, we have now lots of them, about 70 that we have data for. We've only analyzed a few of them yet, because it's a lot of data to process. So now, how does the evolution look like, really? So this is now, has several panels here. You see on the left side, you see some line plots. So what we do here is we take one of these little coronal bright points, and we make a box around it, a very small box that covers just this bright point. And we sum up all the information we have there in case of the intensity images, just the photons. And the 2 top panels you can see of the line plots represent basically the integrated intensity in the corona. The second one in light blue is the intensity as a function of time in the chromosphere, so in 304. And the bottom 2 panels show now the magnetic field. And the magnetic field, as I said, has usually a plus and a minus polarity. So the first panel in blue and red shows you the plus polarity separately and the minus polarity, and how both these magnetic field information, how they change in time. And the bottom panel of the line plots is now, if you add up this magnetic information with a sign, or unsigned. Then if it's unsigned, then you have the total magnetic flux that is changing over time. So the x-axis is time, and it is given in hours. So you can see one of this particular bright point here lives about 30 hours. It's over a day. So let's look at the movies, and I have here the 2D movies. So again, this one here in gray, the first one you see is in 193. The red one is in 304, and the bottom one is the magnetic field information that you have. So this is 30 hours of data, basically 1 image every few minutes that I can show here. So you see there, we start out with basically nothing, and then this bright area comes up. So this is how a typical nice little bright point looks like. It changes all kinds of information, and now it starts to get much bigger. So this was an eruption that you could just see. And then you see it starts fading out, gets smaller and smaller again. And near the end of it, you will see then another one of these eruptive events. Now where we go. And then finally, it is gone again. So let me play this again. And now you can also pay attention not just to the coronal images, you can also have a look at the magnetic field information. And the magnetic field information is in the black and white lower panel. So we start over again from the beginning. And what you can see now, I can point out now in the magnetogram, so when the intensity goes up, you can actually see some black and white bipole coming up. So this is basically the emergence phase of the bright point. And together with the emerging of the flux, both as a bipolar plus-minus region, you can see that the intensity then in the corona and the chromosphere also goes up. So this is the kind of birth phase of this particular particular bright point. Then the magnetic field has emerged. You see that it's suddenly getting compressed and moving together. And while it's moving together, the plus and minus slowly cancel out, and you get less and less and less magnetic field, and at the same time, you get less and less in intensity. So this compression, or this moving together of the magnetic field, is a so-called cancellation or fade-out phase. And this is then eventually when the bright point dies. I would like to show you one other example. So here is basically summary of what I said. So we have a bipolar flux emergence during the emergence phase to give birth to the bright point. And then later we have a cancellation phase where the magnetic field goes away, the intensity goes down, and we also have eruptive events during this phase. Here is a second one that I would like to show. And this is quite interesting because it shows a few different things. The very early phase is very similar. If you look at we start out with nothing, then you can see the bright point coming up, and at the same time you have flux emergence in the magnetic field. So this is kind of very similar to what we had before. So the birth event of this particular bright point has also flux emergence. Then it's just staying there for quite a while and not doing really any much. But you should look in the top part of the panels now, soon. Oh, here we come. So we have another bright point coming up. So there is a little smaller additional bright point that is appearing north of the original one. You see it both in intensity and in the magnetic field. It's actually swept now south towards the main bright point. And as soon as it's starting to interact with that, it starts to set off one eruptive event after the other. So here there was one. And if you go through the whole event series, you can see there are 6 of these jets and 6 of these eruptive events coming up. And every time you see mass that is going to be thrown out, you see magnetic flux is getting less and less. It's canceling out. There's another one. And finally, very slowly, but clearly, the actual magnetic bright point dies out. And eventually, most of the bipolar flux is then gone. As soon as the black and white is gone, at least the white is gone, you see that there's some leftover black flux, but there is no opposite polarity left. And this is when the bright point has died out. So this is insofar very interesting because in the first emergence phase that you can see, it's just the bright point itself showing up. It emits in the radiation in the corona, but it doesn't show any eruptive events. It's only when the second bright point emerges and then coming close enough to interact with the pre-existing structure, only then you actually start to see all the activity. And as you can see, this is an extremely active bright point, so it has 6 eruptive events during the fade-out phase. And this is actually quite a lot. And there's a whole kind of fireworks of jets coming out of this. So this is, for now, everything I wanted to tell you. I wanted to show these 2 examples. We have lots and lots of more. And after analyzing all of them, I think I can then probably give you more conclusive answers on statistics, on how often happens, how many of these jets happen, do we see them in a different way, and so on. Thank you.
Good afternoon. My name is Alexander Kosovichev. And my presentation is about global solar activity, and in particular, phenomena inside the sun. Particularly, my presentation relates to the origin of solar activity cycles. It's been known for a long time that solar activity has a period of sunspot appear with periods of 11 years. But the questions are what process inside the sun controls the strength of these cycles, and how we can predict the future sunspot maxima. And this picture you can see that there were three periods of low solar activity, Maunder minimum, Dalton minimum, and now there is indication that we are going into a new modern solar minimum. And in particular, the solar magnetic field, it shows also interesting patterns. Here you can see the solar magnetic field measured in the past 4 cycles. And in the central of this image, that is formed by a butterfly diagram, it's where the sunspots emerge in the butterfly diagram. At the same time, polar magnetic field also changes with a period of 11 years. And it's been found empirically that polar magnetic field in solar minimum correlates with the strength of the next solar maximum. There is no one-to-one correspondence, but there is a relationship. And our analysis provides an explanation, a butterfly diagram, and this relationship between polar magnetic field and the sunspot cycles. How we look inside the sun, we measure solar oscillations, that acoustic waves. They're trapped inside the sun, excited by turbulent convection, and they form resonant modes. And by measuring frequencies of these modes, we can infer internal structure and dynamics of the sun. And in particular, these measurements that I will show, it's a measurements of zonal flows. It's a stream jets inside the sun. And the general idea is that stream jets are modulated by magnetic fields. So by tracking the stream jets, we can learn about evolution of magnetic field inside the sun. And in this work, the dynamo waves, that the magnetic activity of the sun, global magnetic activity, is controlled by hydromagnetic waves. They call dynamo waves. That waves that are generated by turbulent convection inside the sun and travel through the convection zone. So we track the evolution of these magnetic waves by measuring evolution of the subsurface flows, zonal flows. So this analysis allows us to pin down location where the actual solar cycle are generated at the bottom of the convection zone. And it turns out it happens at the bottom of the convection zone, 120,000 miles beneath the solar surface, and at about 60 degrees latitude. And then these giant waves of solar magnetism, they blast from the bottom of the convection zone, travel to the surface. And here you can see on this picture, you can see that when the cycle 24 started at the bottom of the convection zone, but cycle 23, these blue regions, they show deceleration of these flows. It's progressing on the solar surface at low latitudes, forming the butterfly diagram. Let me show the movie of these waves. They actually been observed since 1996 from 2 NASA spacecraft to measure solar oscillations continuously for more than 20 years. And here you can see the blue arrows, they show deceleration, that where the zonal flows are slowed down by magnetic field. And red shows the acceleration. So this, you can see again how this flows. This picture on the left shows that sunspot number. And you can see that how these waves, they start at high latitudes and then travel down, they migrate towards the equator, and as solar cycle progresses. So this picture again shows that another view of these dynamo waves. And again, so they detected through measurements of zonal deceleration because magnetic field slows down the flow speed. And they originate at the bottom of the convection zone, 120 miles beneath solar surface at about 60 degrees latitude. The red arrow shows here the primary seed of solar dynamo, where the magnetic field is generated, amplified, and then we are able to track migration of the dynamo waves. In this picture, arrow shows that migration that what was tracked on series of images of subsurface flows. And they start what the bottom convection zone called solar tachocline. And the waves, they travel the speed of between 2 and 4 miles per hour. And they reach very quickly the polar regions. In 1 to 2 years, they reach polar regions. But it takes about 10 years to reach the mid-latitudes where the sunspots originate. So this explains this delay, that why these polar regions, the polar magnetic field actually predicts the following solar cycles. Again, that a lot of thing happens once these waves travel to the surface, so there is no one-to-one correspondence that also shown observations. But this is a good indication of the next of the strength of the next of solar cycle. And this picture on the top, it shows again this blue, where the flows are slowed down by magnetic field. And we can see migration with depth. It's a vertical scale here from the bottom convection zone to the surface, and horizontal scale is time. So we can get progression of the current solar cycle 24, where the polar magnetic field migrated towards the surface. And we can see the future solar cycle. It's already appeared in polar regions on the surface, and it's substantially slow. The flows react substantially slowly to the magnetic field. So it indicates that the next solar cycle is likely to be significantly weaker than the current solar cycle. So I repeat the bottom picture here. It shows the sunspot number in the last 2 cycles, and the dash curve shows the flow deceleration 120,000 miles beneath the solar surface. And we already see the next solar maximum there in flows. And here that's a flow deceleration, so it's a negative minima correspond to the solar sunspot maxima. And we can see that it's substantially lower, the cycle 25. So that's an indication that that internal flows indicate that will be further decrease of solar activity, so further decline of solar activity. Thank you.
Good afternoon. My name is Tim Larson, and I am indeed an instructor at Moberly Area Community College here in Missouri. I also got my PhD studying global helioseismology. However, I started the Sonification of Solar Harmonics project with a couple of composers, these guys, Seth Schaefer and Elaine DeFalco. And Rick told you that my presentation is going to be a little bit different, and the main difference is that this is a presentation for everybody. You're going to understand everything I'm about to tell you, and everything I'm going to show you is freely available for download, and all of you can download it and use it. So the oscillations that Sasha was talking about were actually first discovered in 1960. When it was seen that the surface of the sun was moving up and down with a period of about 5 minutes. And eventually it was decided that this oscillation was explained as the result of sound waves trapped in the solar interior. So yeah, that's right. The sun is actually a resonant cavity for really low frequency sound waves. And because these sound waves propagate through the interior, the frequencies tell us about what's going on inside the sun. So although we've been studying this data for decades, we almost never listened to it. But now the SOCH project has developed a software tool that lets everybody do just that. So as I said, the strongest of the sun's harmonics have a period of about 5 minutes, which corresponds to a frequency of only about 3 millihertz, which is far, far below the range of human hearing, which is usually in the hundreds of hertz or maybe thousands of hertz, which is already pretty high. So if you want to measure a 5-minute oscillation, it's common to make a measurement once a minute, which would correspond to a sample rate of 1/60th of a hertz. However, an audio player will not give you any audio sample rate less than about 8,000 hertz. So in this situation, that means that you got a minimum speed up factor of 480,000. And at this rate, a year's worth of data, you could hear it in about a minute, which is one of the major advantages of sonification. However, often this transposition factor is too high, and so one of the things the SOCH tool lets you do is to shift the frequency independent of the sample rate. And as long as you transpose every one of the solar harmonics the same, then the musical intervals between them will be preserved, which obviously is of interest to composers who might want to use the sun as a musical instrument. So back to the science, helioseismology, how it works in general. We start with velocity images of the sun's surface. We decompose each of these images into its spherical harmonic components. More on that in just a second. For each of these spherical harmonics, we make a time series of its amplitude, and then we do an analysis to measure its harmonic content, basically just figure out how much of each frequency is in that time series. And because the different harmonics inhabit different regions inside the sun, here this shows the depth dependence. You can see how some of them stay close to the surface, while others of them penetrate more deeply. And so it's because the different harmonics inhabit different regions that we can use their frequencies to infer things like solar rotation inside the sun. Now, I'm going to play for you a unfiltered time series. This is a single spherical harmonic time series to show you what we're starting with. So this is all the frequency contents playing at once. Not very pleasant to listen to, right? Oops. Okay, good. So the surface behavior of a solar harmonic is a special function of latitude and longitude, which we call spherical harmonics. Spherical harmonics are described by two integers. They're L and M. L is the number of node lines on the surface of the sphere. A node line is simply a place where the amplitude is 0. That's what these white lines in the figure are. And the harmonic degree L tells you how many total are on the surface of the sphere. M tells you how many there are in longitude, and so the number in latitude is simply L minus M. Now, there's also nodes in the radial direction, but of course we can't see that. We only see the surface. So on the next slide, I'll show you some examples of radial eigenfunctions, which give the interior behavior. And they're described by a radial order n, which gives the number of nodes along a radius. So here's two examples. On the left, I have plotted n equals 3, just so you can see it. You can see the 3 circular. You can see the 3, I lost the cursor. You can see the 3 circular node, the 3 node circles. But this mode actually has a frequency that's too low for us to measure. I plotted it so you could see it. Over here on the right is n equals 20. This is a mode we could easily measure, but as you can see, the nodes become too close to each other near the surface to see at this scale. But in any case, the important thing to remember is that the total harmonic will be a product of a spherical harmonic, which is a function on the surface, and this function of depth. It's the two multiplied together that give you the total mode. So here's an example of how the mode frequencies, or how the different harmonics inhabit different regions of the sun. So on the top row, we have the surface view for L equals 25, starting from m equals 0 going across. You can see as m gets closer to L, that the mode stays closer and closer to the equator. And down below, I have the same two values of n, 3 and 20. And you can see that as you go up in frequency or up in n for a given L, that the mode goes deeper. So now, the spherical harmonics, we have a different spherical harmonic for each L and M. But to measure n, we've got to do some Fourier analysis, form a power spectrum. What I've shown you here is actually an amplitude spectrum zoomed in on just one value of n for an L of 10 and M of 0 that I chose at random. So the blue line here is the data, and the orange line is the fit to the data. And so the thing about helioseismology is it works all in terms of mode parameters. So basically, it studies the orange line here. And typically just the peak frequency here is what we use for do helioseismic inversion. We measure the amplitude and the width of this peak, but as you can see, there's a lot more going on here. A lot more information contained in the data than is captured by this simple mode fit. And that's what the SOCH tool allows you to do. It allows you to listen to the actual data that we took. And what's shown here is a good example of a filter window that we might use. So what we do is we zoom in on a mode in frequency space, and we set all the other frequencies to 0, and then we transform back into the time domain. And the result would be something like this. This is, again, L equals 5, M equals 3. And I just picked N equals 17 and 21. These have been transposed by a factor of 135,000 and brings them up to about 375 and 448 hertz. So just an example. So far we've used data from 2 instruments, the same ones that Sasha was talking about, MDI, which took data for 15 years at a cadence of 60 seconds. In 2010, it was superseded by HMI, which takes data every 45 seconds and is operating still today. And now MDI has been sonified sporadically in the past. In fact, by Sasha himself, was the one who most famously did it. But now that can be done interactively. And so far, the SOCH project is the only people who have sonified HMI data and the only sonification of 2 full solar cycles of data spanning both instruments. So moving forward, already available is the SOCH Pi visualization package. It made most of the figures that I've showed you. We're developing a mobile app to give people a way to explore the way the amplitude of modes varies inside the sun. My collaborators are working on planetarium presentations in virtual reality environments where you can, with ambisonic audio, to like spatially separate the different modes. My own personal ambition is to maybe use some of the experience I've got in sonifying global helioseismic data and maybe use it to sonify local helioseismic data. And so maybe one day it could be possible to hear a solar flare. But very soon, what's coming up real soon is we're going to be flooding SoundCloud with all kinds of nature sounds, but of the sun. And so very soon we will find out just what people can hear in it. Thank you very much. All right, I'm always losing the cursor.
Okay, thank you guys very much. All right, we'll go to questions. We'll start here in the room, and I'd like you to wait for a microphone. I'm being assisted here with the mic by Trey Winter. He is the Solar Physics Division's volunteer press officer. So wait for the mic, and when you get it, please identify yourself and tell us who you're asking a question of, and then we will go to the webcast. Okay, questions here in the room? All right, start here and then go down the line.
So, Sanjiv.
Can you please tell us who you are?
I'm David Rabahi from Michigan. The question I have is, if we could have an instrument up longer than just 5 minutes, that would be a useful thing?
Yes.
Okay, so is it only you have to clear the atmosphere, or is it like orbit? Where would be an optimal place for an instrument that would be measuring continuously?
Yeah, so there are already some instruments like Solar Dynamics Observatory. It's giving every 12 seconds there is coronal data available in multiple wavelengths. So there are different places, like L1 is one, there are instruments, and there are other places where, which could be geostationary, basically. There are so many satellites. So those can be observing sun almost all the time. And this is already happening. This is the images that Karin also showed actually, and I also showed full disk solar image. So that is continuously, we are getting those images continuously, but the idea was to see really smaller scale structures, in fine details what is happening. And for that, of course, there are some technology limitations that we don't have yet for full disk, that kind of images.
Yes. Thank you.
Thank you.
Okay, over here.
Daniel Deveau, Canada France Hawaii Telescope. My question is for Alexander. You mentioned that you predict a lesser solar maximum for cycle 25. How much less is it going to be? Do you have an idea of the order of magnitude?
It's the flow measurement. It shows that roughly a half, maybe
Half,
60%, yeah, of current solar cycle.
And from that and other data, can you predict it? Can you predict better if we're going to a minimum, and how much this minimum is going to be?
Well, currently the best predictions are made by comparing with polar magnetic field. I believe he'll be on Wednesday. Will be a press conference about this, about prediction based on polar magnetic field, and our prediction is made first by first prediction made by measuring something inside the sun, by measuring the strength of subsurface flows. And here uncertainty, one of the uncertainties is that these flows interact with magnetic field in a turbulent environment. And we still don't quite understand the relationship between these. So there is strong indication that the next solar cycle will be weaker. But how much, it's difficult to say.
It's hard to say. Okay, thank you.
Andrew Fracknoy, freelance. I have a question for Timothy. I'm asking this as a person who catalogs astronomical music on the web. I was, at the end, a little confused. Will this actually turn into music? You mentioned your co-authors were composers.
They are both composers.
So what is their role in the project? And tell us more about how this is something that might lead to music.
Well, I've been trying to get helioseismologists interested in this for quite a while, completely failing. And it was brought up to my attention again by actually Elaine DeFalco, who was composing something for a master's thesis at the time. But they turned me on to this new free software platform. It's called Pure Data. It's a visual programming language. A lot of musicians use it for live performances, but it's free, and it comes with this graphical interface. And so that is actually what the Soch tool is written in. Anyway, and so once I had this little start, then I've really just run with it. And it's actually taught me a lot about what a solar mode is, and how it is that we analyze the data. I mean, it's pretty complex. And actually, I've designed the Soch tool to really closely mimic the steps in the scientific global helioseismic analysis. So we really are listening to the data that we analyze. So we take the Fourier transform over 72 days, which you would never do to listen to it. But I do that to preserve the full phase information, so when you start adding modes together, which is another thing the Soch tool lets you do. It lets you listen to these modes singly, and it lets you add them together, concatenate them. So there's a lot of different tools in the package, and you can write music with it, but you can also hear physical effects like solar rotation. You can hear the small frequency separation in it, which tells you a little bit about the solar core. There's different things that, we're just now starting to explore the sound space.
So would the sun get a songwriting credit?
Maybe.
Any other questions in here? Not right now. Do we have any on the web? Okay.
Okay, this is a question from Rick Lovett, freelance for Karin. Is the goal of this to get closer to predicting big flares and CMEs? And if so, can you elaborate on how this scales up or how you will be working to scale it up?
Yes, so the idea is definitely to find out at what stage in the life of an active region can we expect flares and CMEs. As I said, by downscaling it and looking at coronal bright points. And what we've seen up to now already, it seems like in the emergence phase, there is not much going on in terms of eruptive events. And if you look at the literature, a lot of the numerical models that exist for these jets actually do model these eruptive events in the emergence phase, which seems not very, at the moment, compatible with our observations. But again, I haven't looked at enough events to make a firm conclusion on that. In the end, yes, we would like to see if we can scale this up to the larger events, especially flares and CMEs. And what I think I can do most likely is figuring out what's happening in the photosphere that might be a driver or what might be the trigger for these events. I think, again, the coronal response is happening much higher up, and you can look at that in the coronal events are very quick. So you can use snapshots for that. But how to build up the energy, that is something that's happening longer term, and you can then look, in this case, in the photosphere and the photospheric drivers in a much better way. And as I said, we have coronal images. We can also use the stereo images, which allow us to look at the corona on the far side, so when the thing is rotating off. But we cannot look at the photosphere as soon as the active region has rotated off. And so that's the biggest advantage of using looking at the small scale regions.
Anything else? I have a few questions. So my first question is for Sanjiv and Karin. You both talked about points, but I gather that you're talking about points of different scales and different durations. But I'm wondering if you can expand a little on, sort of what are the relationships or the differences between the two different kinds of brightenings and small features that you're looking at, and what, if anything, you've been able to tell from looking at them that they might contribute to heating the corona, or is that just an unrelated issue?
Yeah, so as you said, yes, they are at different scales. So the dots that I showed, they are, as I said, they are just even smaller than 10 times smaller than Earth radius. Their radius is that is small. So what Karin was talking, those active regions, tiny active regions, are small active regions in the beginning of flux emergence that she showed. They look like dots, not dots, but they are known as bright points, basically. They are really huge. They are still, I don't know, maybe 100 times, not 100 times, but about 10 times maybe bigger than our dot-like structures, yeah.
Comparable in size to Earth, it sounds like, roughly?
Yes, roughly.
Yeah, it's about size of the Earth, or a few times size of the Earth. So.
Yeah, so 10 to 20 times in that range. So those are slightly different because these events are not exactly formed due to flux emergence. So that is the basic difference I see. And what bright point C sees, those are due to flux emergence. And what we see is due to flux cancellation. So that is what we interpret. So there are fundamental differences, and we think that most of the heating that we have other studies also in the past, and we find that most of the heating in coronal loops, bigger loops, or even tiny scale things, those are related to flux cancellation mostly. Although when flux emerges, you have bright points, but the more transient events, which have lifetime of 1 minute, 2 minutes, and that range, or 3 minutes, even larger ones, some of them, they are mostly when there is flux cancellation and magnetic topology suddenly changes. So those are more transient ones.
Okay. And when you use the term flux cancellation, what's the relationship between that and a term that I'm more used to hearing, magnetic reconnection? Is it the same thing, or is it two different things?
So flux cancellation happens on the surface of the sun. And reconnection, magnetic field lines, reconnection happens mostly in the corona, higher into corona. So when you have two field lines, let us say, and they reconnect, they form two other field lines, smaller one and another, which can be larger often. So the smaller one gets, because of stronger magnetic tension forces, often that gets submerged into the photosphere, and that is what flux cancellation is.
Okay.
So reconnection often happens in the higher atmosphere, and higher corona, or chromosphere, but flux cancellation is different when you see flux disappearing on the surface. These are related.
Okay, but
yes.
It's opposite polarities of magnetic field that's at the core of what's going on in both cases, it sounds like.
So
I'm trying to understand because I don't really know solar physics.
No, sure. So flux cancellation, you have opposite polarities fields which have to be together and shared to disappear, to cancel with each other and disappear. But for reconnection, you don't need to have that. For example, there is nanoflare mechanism proposed by Parker, and he doesn't require flux cancellation. So basically, you have field lines in corona, you have braiding. And these braiding, because you have convection, so these braided structures can reconnect slowly or fast. They can be fast also, but nanoflares are really slow. These are ohmic dissipation thing. So they can reconnect there without requiring mixed polarity field. Okay. So these are, reconnection is basically in two field lines. If there are two field lines like this, and they meet somewhere, if there is enough tension in them, magnetic energy can be released by reconnection, and then it is hot, it is bright, it dissipates magnetic energy. Mm-hmm. So that is reconnection. It doesn't require mixed polarity field. Okay. Anything else online? Okay, got another question coming from the webcast.
Question for Timothy from Doyle Rice at USA Today. At a very basic layman level, what is it that we were hearing when we were listening to the sun sounds?
You are the motion of the sun's surface. Cool. That's the short answer. I mean, we take these images of the sun, we decompose them into their components, which is like a spatial filter that like you're putting a spatial filter onto the surface of the sun, and then you form a time series using that spatial filter. And then you can do a frequency analysis that lets you put a frequency filter on, and then that was the last thing that we heard. So the first thing that I played for you was just the spatial filtering, no frequency filtering. And then I took that same thing and applied frequency filtering to pick out 2 of the peaks in it.
Okay, we have one. Trey, do you still have a mic? Thank you.
David Rabahi of Michigan again. I'm curious if it's possible to create these magnetic effects in the laboratory, or do we just can't make strong enough magnetic fields? How's that work?
There are some laboratory experiments. So there are some MHD simulations. Basically, there are also some experiments going on, but more MHD simulations are there in big computer. You use, of course, require big computers, and then you can reproduce by using all those MHD equations. You can reproduce small-scale reconnections. So that we are able to see. There are some simulation groups who have actually very efficiently, although they don't start from the scratch, that is the problem. There are some where you have, they can produce magnetic field lines, and then they twist it not manually by known process, and then they relax it. So there are some reconnection that happens in that way, and they try to understand how much energy is released and so on. But yes, there are limitations. Of course, we don't have that. Sun is our closest laboratory. We don't have anything of that size that we can do on the Earth. But there are different things like Reynolds number is a parameter that cannot be optimized in any laboratory. So there are similar other limitations that we cannot really produce the same thing. But yes, there are efforts on MHD simulation side that they are trying to reproduce some of those. They are getting closer in many cases. There are some real MHD simulations of sunspots, for example, and they are now extending it to corona. So their physics is more complicated, but there are works going on, yeah.
Thank you.
Okay, well, it's about 4 o'clock, so I think we should close out the briefing. I want to thank our speakers again for their very interesting and audible presentations. We could hear it. And I want to let the press corps know that there's, I think, just one press release going out from this briefing, but that should be winging its way to you shortly if it hasn't already arrived via the AAS press list. Tomorrow we will have 2 more briefings. The first one tomorrow morning at 11 Central Time here is on spiral galaxies near and far. And then the next 2 briefings after that will feature more results from Solar Physics Division related papers. So there's going to be yet more of what's new under the sun. So thanks again for coming, and we look forward to seeing you tomorrow. Bye-bye.